So even though we studied Chapter-12, exam 1 only have Chapter-9, Chapter-10, Chapter-11. So I think most of the exam on Tuesday. So I think.
And then Monday we're here until 45.
Yeah. So see, Monday we only have like about 2 hours. We have a little more time to start. Yeah. Monday we have a quiz on Chapter-11. I'll try. Yeah. That's right. I also trying to be towards the kind of project. Yeah. Yeah. So all. I think just a little, too many reactions. So I think all the reactions you saw on the lecture notes, you saw like in the homework, right? It's pretty much all of those homework questions, all those lecture questions on the exam. Yeah. No. About 1 hour. I think about 1 hour.
How many questions?
How many questions? I think about 25, 27 questions. Each question might have like even more questions. You do 7 to 8 questions in 20 minutes, right? And so then 1 hour you divide by 24 questions.
1 hour 60 minutes.
Yeah. All 3 parts. Yeah, each step like this participant has first person has 3 areas. You use like one region, you get a second region right, you get the third right. I'll give you back probably like if you want to get back tomorrow or Sunday. If you want to study for the exam, I can even come and otherwise, I might scan you. What I was thinking also, you just study those, you pretty much just re-study those lecture notes and homework. Not exactly what those that fashion.
We'll get it by Monday though.
Yeah.
It's just a look over it.
Yeah, just look it over and reading those lecture notes, read the homework. I said you probably get a rough first week start because you don't have time to prepare before the class. Now the second week you can get the time to prepare, right? The weekend, and I think the weekend you can prepare like for the next week.
Do you further exams?
So the exam no further. We have the. Just about 27, 25 questions, and each question have some points. You get a part of credit if you, as I said, if you get 1 step right, you miss the second step. You name it. If you name it, you get the right location for the pure bomb, and at least you get the any Y and E, and you might get the method different places.
Every column right down every This is an arrow. Bring a power through.
Okay, so I think I talked to Professor Troutman, and he said temperature will be down temperature. Another temperature we're waiting like the temperature 20. So color temperature is always dependent on. There's a lot of this one of them. And okay, so in this temperature you will see a lot of reactions that will make the product looks like you get some of those side chain or some of those substitution on the bending. I think it's an interesting temperature. It seems to me, after some time, I still remember this Electrophilic and Nucleophilic aromatic substitution. So it's pretty much a substitution compared to what you did before addition. Because if you do the substitution, you still keep the bending rings aromaticity. And that will make your transition state much easier to smooth the activation and resolver. Otherwise, if you like totally break the aromaticity, even though in the transition state you break part of that, but you don't break all, but there's still somewhat influence your transition state overall. Let's first study the 5 common representative electrophilic aromatic substitution reaction of benzene. And the first one is nitration. And these 5 reactions, you can get those patterns. But you first see what is your overall reaction and what is your electrophile. Then you first see how you generate the electrophile and what is the product. Right now the product is relatively easy because you start with the benzene ring, nothing on it, and just put this one substituting the group at any place. So this overall reaction, and usually for this reaction happen at reasonable speed, and you need to add the sulfuric acid, and let's see 30 to 40 degrees Celsius, a little warmer. And then you produce mononitrobenzene and plus H2O. We have in the so-called electrophilic aromatic substitution, and we have to see what is our electrophile. Our electrophile is NO2 plus, and the Lewis structure for this NO2 1 plus is like this. So each atom in this ion has an octet. But if you calculate the formal charge, the nitrogen atom is 1 plus. And that is the atom, the plus ion reside on. So where is the plus ion? Where is the plus charge? In the middle nitrogen atom. So how you produce that? Starting from nitric acid and sulfuric acid. For sulfuric acid, if you examine the pKa from the table, and you see that it is even a stronger acid than the nitric acid. So therefore, it can protonize your nitric acid. Here again, that is a relatively plus, and it has a negative charge, negative formal charge. Okay, so what happens is this lone pair here, and the broken electron like this. So then this will give you HOSO2O3, one negative, and plus O and H. That only have this water can be a living group. So these electrons can get on that, and then this electron can come back and produce our nitrogen ion electrophile and plus water, even though water is not important. So this is how we produce this guy. So these two guys are the same, nitrogen. Then this nitrogen ion is really very electrophilic because it has a positive charge. Let me just draw one H out on the painting. And you have this N has the positive charge. Really electron efficient. Okay. So what it do, it will grab some electrons from the bending ring. Even though we know bending ring usually very stable, not that active. Okay. So this is very slow. But because this N is so electronegative, so much like electron hanger, okay, it will grab the electron from the bending ring. So therefore, you bring one to the bond there, and you still have that other H there. Okay. Now you are bonding this. And this guy still has a positive charge. So overall, you still have one positive. On the left side arrow, you have one positive on the N, in the nitrogen ion. On the right side, you still have one positive, and you have two positive, one negative, you still have one positive. Alright. So these will be the typical reaction mechanism in this 5 reaction. Just what will be different, how we will be different on this guy. Okay? So once you produce something like this, okay, so you break the aromaticity. You see, you don't have a double bond here anymore. You only have these two contributed double bond. Okay? So you don't do like the addition. You do the addition, you add on this and you add on somewhere here. You totally break the aromaticity. The next step, you are going to building up the aromaticity in the bending ring. So cross chapter here, and this N, O. And cross here, 2 electron here, negative, then H here. Now this water as a base, and take the proton away. Then this 2 electrons from the carbon H bond, it can go back to the bending ring. So that will give you a very quick reaction. cross H3O cross. Any questions? So one very good practice is you are going to do a nitration on aromatic compound, not simply benzene this time. You 1,4-dimethyl benzene because the P is lining. Okay? And let's see what is P is lining or 1,4.
Can you go back for a second? Just one second.
Let's see what is 1,4.
Thank you.
Welcome. What is 1,4-dimethyl benzene? There's methyl, right? 1,4-dimethyl benzene. Now remember the substitution is the substitution at the place that is on the benzene and with the H atom, right? So if you have this H angle 3, then what is the catalyst is H2SO4. So these two pair of acids produce our N, our nitrogen ion, like that. So the middle one, nitrogen is positive, very, very electron hanger, positive cation. Okay? So it will replace substitute H on the benzene ring. Okay? And sometimes you have a choice which H you want to substitute. There's no H here, no H here, because this carbon, both of these carbon already have a 4 bond. Right? There's H here, H here, H here. If you want to see clearly this 4H, for this example, the 4H are equivalent. Right? Can you tell the difference between the 4H? They're all the same. For example, this H is closer to one methyl and like meta to the other methyl. Also to one and meta to the other one. And the same for this one. Right? They are all the same. This H is also to this methyl and meta to the other methyl. And this one also to this, meta to that. There's no difference between these two methods. So when you do a nitration, your first nitration means you substitute this structure 1H by NO2. Now let's do a practice. This a problem 12.3, and want you to use the curved arrow show the flow of electrons. If you start with this P styling, you know your electrophile is nitrogen ion, right? What's the question, Ollie? Any questions? You get an answer now to the question? So this is the slow step. Yeah? I just draw, let's say, draw one H out. Yeah? Draw one H out. Obviously, the other four H, but all the four H are the same. Okay? And what you do is like what did before in the other mechanism. Okay? So electron from one bond come here, okay? And you produce remember right now this intermediate don't have the aromaticity anymore, right? So it try to restore the aromaticity by loss of proton. So next step is kind of acid-base reactions, loss of proton. On mechanism, on the exam, I will use the hint. The loss of proton or add proton. And you just know which proton will be the easy one to get lost, which one will be what place is the easiest place to add on. So you take the intermediate or the product from your first step. Make sure you have these two methods. And now you have that H and this nitro group. Cross chapter here, compare negative. And you remember what you use in this time, you can use water as the base. So this water has long pair electron. Okay. And let me change to red, so easy to see this. So here is the plus for that. Here I think that's very easy. So here is the plus. For that. And this electron pair from the bonding between H and C will get back to the bending ring. Now you restore the aromaticity, okay? But in the same time, you lost one H. And here's the plus. Okay, so you produce the H3O plus again. Any questions? So next reaction, you will see the pattern is similar, so therefore the mechanism is very similar. Okay? So the sulfonation. Okay? Sulfonation is the overall reactions is like this. You adding those concentrated sulfuric acid together with a benzene compound. So this is our overall reaction. Our electrophile is the sulfur trioxide. You can think about the electrophile with either resonance structures. Probably you need to think about the level one, because the level one clearly indicating you have that so you have that cross charge on sulfur. Right? How you produce this? Sometimes just power in some of those sulfur trioxide, or you can produce the sulfur trioxide from the concentrated sulfuric acid. What happened like and then this pair of electrons transform to O. So from the left side H, so here you will produce H plus, and here you will produce OH negative. So kind of a dehydration of a sulfuric acid. So you produce sulfur, and initially have that O on the top, and you initially have this O at the bottom, and you have the O on the right side, the left side, initially single bond, and then becomes double bond. Okay. So then you will see the OH and together with H plus produce water.
Why is it becoming a double bond?
The double bond comes from initially you have a single bond here, and this pair of electrons come over, produce the second bond. And this electron here initially on between sulfur and oxygen disappear, and again on this O.
I get it now. Because I was looking at the one connected between the hydrogen and the oxygen, the bond between that. That's why I got confused.
Here we will see from this side we produce this H plus. If this electron disappear, then this H plus will separate. And same right here. If this electron, found electron, you take away, and that becomes OH negative. Right? So say again, say if you take this electron away, take this electron away, this becomes H plus.
Yeah.
If you take this electron away, these two become OH negative. Then OH negative H plus become water. Okay? So then this can resonance with that. You can use this derivative to like as electrophile. Easier to visualize this one as electrophile. Electrophile helps with those positive charge, and so easy to see that. That's repeating the mechanism, and it's a very similar mechanism as you see for the nitrogen. Okay, I will just only draw one H out, right? So let's draw the electrophile as this, as one of those resonance structures. So we have this negative here and a positive here. Okay. Because sulfur right now is kind of partly positive charge, so that can attracting the electron from the blinking ring. And then you will have a very slow process. So this will give you you will have two negative oxygen. And to see the other oxygen become negative, you can add one arrow here. Adding electron, sometimes I forget to have those electrons initially. Yeah.
There's a double bond.
Where is the double bond? Yeah, there are two double bonds.
No,
Right?
last one.
Last one, there's only one double bond.
Right now.
Oh, right.
Yeah.
Right. That's right. Alright, so let's continue finish. I think the next step you should know is what being negative here, and positive here. So we'll forget the positive here too. questions? This time, you can still take the water as base and take the electron away from here. You did not show the, let's see, let me show the process inside the ring, so not continuous. So the process here. And you see that this two pair of electron on the oxygen in water, and that the oxygen use one pair to take the proton away from that. Then these two electrons it will go back to the benzene ring. So now we have this intermediate. Because right now you have this anion, and you are in the environment that is acidic, because it's starting from this sulfuric acid. It will protonize very quick. We have this, let me check, we have all the long pair. But sometimes, because those oxygen not in the chemical reaction, and you don't have to worry about their long pairs too much. So there's a lot of sulfuric acid. And sulfuric acid will transfer the proton very quick onto water to make those kind of hydronium ions. Okay? So then one of these first going to grab this proton